You now know about the stochastic gradient descent algorithm, but when you're running the algorithm, how do you make sure that it is sort of completely debugged and it is converging okay? And equally important, how do you tune the learning rate alpha for stochastic gradient descent? In this video, we'll talk about some techniques for doing these things, for making sure it's converging, and for picking the learning rate alpha. Back when we were using batch gradient descent, our standard way for making sure that gradient descent was converging was we would plot the optimization cost function as a function of the number of iterations. So that was the cost function, and we would make sure that this cost function is decreasing on every iteration. When the training set size was small, we could do that because we could compute the sum pretty efficiently. But when you have a massive training set size, then you don't want to have to pause your algorithm periodically. You don't want to have to pause stochastic gradient descent periodically in order to compute this cost function, since it requires a sum over your entire training set size. And the whole point of stochastic gradient descent was that you wanted to start to make progress after looking at just a single example without needing to occasionally scan through your entire training set right in the middle of the algorithm just to compute things like the cost function over your entire training set. So for stochastic gradient descent, in order to check that the algorithm is converging, here's what we can do instead. Let's take the definition of the cost that we had previously. So the cost of the parameter theta with respect to a single training example is just 1/2 of the squared error on that training example. Then while stochastic gradient descent is learning, right before we train on a specific example, so in stochastic gradient descent, we're going to look at the examples xi, yi in order, and then sort of take a little update with respect to this example, and then go on to the next example, xi plus 1, yi plus 1, and so on, right? That's what stochastic gradient descent does. So while the algorithm is looking at the example xi, yi, but before it has updated the parameters theta using that example, let's compute the cost of that example. Just to say the same thing again, but using slightly different words, as stochastic gradient descent is scanning through our training set, right before we have updated theta using a particular training example xi, yi, let's compute how well our hypothesis is doing on that training example. Okay, and we want to do this before updating theta, because if we've just updated theta using that training example, then it might be doing better on that example than would be representative. Finally, in order to check for the convergence of stochastic gradient descent, what we can do is every 1,000 iterations, we can plot these costs that we've been computing in the previous step. We can plot those costs average over, say, the last 1,000 examples processed by the algorithm. And if you do this, it kind of gives you a running estimate of how well the algorithm is doing on, the last 1,000 training examples that your algorithm has seen. So in contrast to computing JTrain periodically, which needed to scan through the entire training set, with this sort of procedure, well, as part of stochastic gradient descent, it doesn't cost much to compute these costs as well right before updating the parameter theta. And all we're doing is every 1,000 iterations or so, we just average the last 1,000 costs that we computed, and we plot that. And by looking at those plots, this will allow us to check if stochastic gradient descent is converging. So here are a few examples of what these plots might look like. Suppose we were to plot the cost average over the last 1,000 examples. Because these are average over just 1,000 examples, they are going to be a little bit noisy, and so it may not decrease on every single iteration. But if you get a figure that looks like this, so the plot is noisy because it's average over just a small subset, say 1,000 training examples. If you get a figure that looks like this, that would be a pretty decent run of the algorithm maybe, where it looks like the cost has gone down and then it's plateaued out, it's kind of flattened out, starting from around that point. So it looks like if this is what your cost looks like, then maybe your learning algorithm has converged. If you were to try using a smaller learning rate, something that you might see is that the algorithm may initially learn more slowly, so the cost goes down more slowly, but then eventually with a smaller learning rate, it's actually possible for the algorithm to end up at a maybe very slightly better solution. So the red line may represent the behavior of stochastic gradient descent using a smaller learning rate. And the reason this is the case is because you remember stochastic gradient descent doesn't just converge to the global minimum. Instead, what it does is the parameters will oscillate a bit around the global minimum. And so by using a smaller learning rate, you end up with smaller oscillations. And sometimes this little difference will be negligible. And sometimes with a smaller learning rate, you can get a slightly better value for the parameters. Here are some other things that might happen. Let's say you run stochastic gradient descent and you average over 1,000 examples when plotting these costs. So, here might be a result of another one of these plots. And again, it kind of looks like it's converged. If you were to take this number, 1,000, and increase it to averaging over 5,000 examples, then it's possible that you might get a smoother curve that looks more like this. And by averaging over, say, 5,000 examples instead of 1,000, you might be able to get a smoother curve like this. And so that's the effect of increasing the number of examples you average over. The disadvantage of making this too big, of course, is that now you get one data point only every 5,000 examples. And so the feedback you get on how well your learning algorithm is doing is sort of, maybe it's more delayed because you get one data point on your plot only every 5,000 examples rather than every 1,000 examples. Along a similar vein, sometimes you may run stochastic gradient descent and end up with a plot that looks like this. And with a plot that looks like this, it looks like the cost just is not decreasing at all. It looks like the algorithm is just not learning. It just looks like basically a flat curve, and it's just the cost is just not decreasing. But again, if you were to increase this to averaging over a larger number of examples, it's possible that you see something like this red line. It looks like the cost actually is decreasing. It's just that the blue line, averaging over too few examples, the blue line was too noisy, so you couldn't see the actual trend in the cost actually decreasing. And possibly averaging over 5,000 examples instead of 1,000 may help. Of course, when you average over a larger number of examples, if you were to average over 5,000 examples, I'm just using a different color, it's also possible that you see that the learning curve ends up looking like this. That it's still flat even when you're averaging over a larger number of examples. And if you get that, then that's maybe just a more firm verification that unfortunately the algorithm just isn't learning much for whatever reason, and you need to either change the learning rate or change the features or change something else about the algorithm. Finally, one last thing that you might see would be if you were to plot these curves and you see a curve that looks like this, where it actually looks like it's increasing. And if that's the case, then this is a sign that the algorithm is diverging. And what you really should do is use a smaller value of the learning rate alpha. So hopefully this gives you a sense of the range of phenomena you might see when you plot these costs average over some range of examples, as well as suggest the sorts of things you might try to do in response to seeing different plots. So if the plot looks too noisy, if it sort of wiggles up and down too much, then try increasing the number of examples you're averaging over so that you can see the overall trend in the plot better. And if you see that the errors are actually increasing, the costs are actually increasing, try using a smaller value of alpha. Finally, it's worth examining the issue of the learning rate just a little bit more. We saw that when you run stochastic gradient descent, the algorithm will start here and sort of meander towards the minimum, and then it won't really converge, but instead it'll wander around the minimum forever. And so you end up with a parameter value that is hopefully close to the global minimum, but won't be exactly at the global minimum. In most typical implementations of stochastic gradient descent, the learning rate alpha is typically held constant, and so what you typically end up with is exactly a picture like this. If you want stochastic gradient descent to actually converge to the global minimum, there's one thing which you can do, which is you can slowly decrease the learning rate alpha over time. So a pretty typical way of doing that would be to set alpha equals some constant 1 divided by iteration number plus constant 2. So iteration number is the number of iterations you've run of stochastic gradient descent. So it's really the number of training examples you've seen. And const 1 and const 2 are additional parameters of the algorithm that you might have to play with a bit in order to get good performance. One of the reasons people tend not to do this is because you end up needing to spend time playing with these two extra parameters, const 1 and const 2. And so this makes the algorithm more finicky. It's just more parameters that you need to fiddle with in order to make the algorithm work well. But if you manage to tune the parameters well, then the picture you can get is that the algorithm will actually meander around towards the minimum, but as it gets closer, because you're decreasing the learning rate, the meanderings will get smaller and smaller until it pretty much just converges to the global minimum. I hope this makes sense, right? And the reason this formula makes sense is because as the algorithm runs, the iteration number becomes large, and so alpha will slowly become small. And so you take smaller and smaller steps until it sort of, hopefully converges to the global minimum. So if you do slowly decrease alpha to 0, you can end up with a slightly better hypothesis, but because of the extra work needed to fit up the constants, and because frankly usually we're pretty happy with any parameter value that's pretty close to global minimum, typically this process of decreasing alpha slowly is usually not done, and keeping the learning rate alpha constant is the more common application of stochastic gradient descent, although you will see people use either version. To summarize, in this video we talked about a way for approximately monitoring how stochastic gradient descent is doing in terms of optimizing the cost function. And this is a method that does not require scanning over the entire training set periodically to compute the cost function on the entire training set. But instead it looks at, say, only the last 1,000 examples or so. And you can use this method both to make sure that stochastic gradient descent is running okay and is converging, or to use it to tune the learning rate alpha.